Yeah, thank you very much. It's very nice to be here. And today I'll be talking about fuel cells basically. But here on the slide you see also hydrogen. So I will actually skip through this. So these are the learning outcomes of today's lecture. The first part is hydrogen, which I will actually skip. Then I will mainly talking about fuel cells. So I just wanted to show, like I think like last lecture you have already heard about hydrogen and how it's used. So I think you have already understood. The main point there is the hydrogen as a fuel. The point is where is the energy? For example, when in a solar cell we are converting light into electricity. So when in a fuel cells or in a fuels, where is the energy? So energy is in the chemical bonds. So when we have chemical bonds, so when they break, we get energy. So that's basically where the hydrogen carries energy. So I skipped that part and I jump directly to fuel cells. Okay, so let's start with this one. So the first point is what is a fuel cell, how it works, and what are the applications and what are the trends in markets. So we will be mainly focusing on how fuel cell works. So we will go in detail about its working principle. And there, if you happen to have any question at any point related to presentation or anything else that you have in your mind, just ask directly. So do not wait till the end of the lecture, just ask any questions that you have. So what is a fuel cell? A fuel cell is basically an electrochemical device that convert the chemical energy in the fuel that you have already studied in the last lecture, convert that chemical energy in the fuel into electricity. For example, here you see one schematic, and there you see that hydrogen is coming, and at one electrode, oxidation reaction happens, and as a result, we get protons. This hydrogen is split into protons, and our electrolyte layer or proton exchange membrane, it's electrically insulator. It doesn't allow electrons to pass through it. Only ions can move through it. So when this hydrogen comes to one anode, which is an electrode, this hydrogen gas, it splits into hydrogen ions and pass through this proton exchange membrane. Electrons cannot pass through it because it's electrically insulator. So electrons pass through the external circuit where we have the least resistance, the electrical wires. And on the other side of the fuel cell where we have cathode, there what happen is reduction reaction happen. So basically these protons, they react with oxygen ions and they form water. So that's overall reaction. If you look at here, that basically we have two molecules of hydrogen, we have oxygen, and we get water. So, and we get electricity there. So the only byproduct of fuel cell is water, which is clean. So water is not undesirable thing. So, and we get electricity. So fuel cell is a clean energy technology. And for example, if we burn fuel, that's a combustion. So we can also get energy. But if we want to make electricity from burning, we have to convert that energy first into some mechanical energy with the help of generator, then we can make it into electrical energy. So there are lots of losses, and overall efficiency of that process is 10 to 15%, very low. But the good thing about fuel cell is that we can convert up to 60 to 70, ideal is 80. So we convert that amount of energy into electricity. So losses are much less. So this is more efficient way of converting fuel into electricity. So that's the first thing. Yeah, please.
Can you always use this device in opposite directions? So can you take water and make hydrogen?
Yeah, actually this is a very popular way these days, that in some of those, because in fuel cells there are different types. In some of those types, those materials, they are actually quite efficient way that you give electricity and you get water. So it's just the same thing in the opposite direction. And in our group, we are working on this solid oxide ceramic materials, and those are actually quite good for that purpose. And I will actually later in some of the slides, I will briefly talk about that thing also.
On Monday, we had a discussion that this hydrocell should generate some heat.
Yes.
Is it general principle?
Yeah, it generates heats also. Especially, we have different kinds of fuel cells, and especially we have a high temperature solid oxide fuel cells, and there we get lots of heat also. And that heat can be also used. So it can be heat plus electricity, or we can use that heat also to generate further electricity. So there are different ways. So we get electricity and heat. Yeah. So a little bit of history about fuel cells. Fuel cells were basically electrolysis, which is kind of the opposite of how fuel cells work. They were already there in 19th, in the beginning of 19th century, but in 1839, or at that time, it was Sir William Grove. He invented this idea of fuel cells. So he demonstrated the concept there. But it took about 100 years. No commercialization, nothing happened in 100 years. But after 100 years, then comes our Francis Thomas Bacon. And he was the first person who started using these devices for some practical purposes. And the first project was actually from NASA. And the NASA, they were trying to reach moon at that time. They were sending different satellites. So Apollo 11, the first satellite that reached moon, that was also uses fuel cells, and the fuel cells were basically powering their electronics in the satellites. So that was like the first application. Those were a specific type of fuel cells called alkaline fuel cell, but those were fuel cells that were used in the satellites. And over the period of time, now we have applications from small size, few watts, to megawatts application nowadays. So that's a very brief history about fuel cells. And I always think about fuel cells as sandwiches, basically. So we have two slices of bread, and then we have something in between. So depending on what you fill in between a sandwich, if you fill tuna, it becomes a tuna sandwich, or if you fill it with some only cheese, it's a cheese sandwich. So depending on what you fill inside, it depends its type. Similarly, in fuel cells, we have different types, and depending on the materials that you use, especially the one which is in between. So we have one electrode on one side, the other electrode on the other side, and electrolyte in the middle. So depending on what electrolyte you use, it depends the type of the fuel cell. For example, we have polymer exchange membrane fuel cells, the first bottom one, which operates at lower temperature. Then we go to phosphoric acid. So only one material is changing, and the operating temperature is changing, working mechanism slightly changing. And the working mechanism overall is kind of the same oxidation reduction reaction happens, but the ions which can move in the middle layer, they vary. For example, if you go to the most popular one nowadays is solid oxide fuel cell, and there you see oxygen ions are actually moving in the middle layer, the electrolyte layer. So, but if you look at the operating temperature, they are operated at very high temperatures, which has advantages and disadvantages, because when they operate at very high temperature, the problem is degradation reactions can happen, and we have limited choice of materials because there are not many materials which can be stable at that high temperature. So that's why ceramic materials are used for that purpose. And but the good thing is, yeah, please.
What electrolyte would you choose if you want to build an automobile?
Automobile, yeah, I think for most of these automobile applications, the lower temperatures are used, because one of the disadvantage of the higher temperature ones is long startup time. Because if you have in a vehicle and you are using very high temperature fuel cell, it will take time before heating it up and it starts operating. So startup time will be longer, although there is work going on also for transport application. But I think the dominant technology is PEM fuel cell for transport application. The high temperature ones are mostly for stationary applications. So that's more typical.
Is there any mechanical devices for heating fuel cell if you use polttokennoista in winter?
Yeah, so some kind of, you mean for the high temperature fuels?
If you start your engine in
Yeah.
Finland in winter, which is about 20 degrees below zero,
Yeah.
you need to heat that.
Yeah, and I think that's kind of easy, because then basically what we, in those kind of setups, usually it's like burning of combustion of the gases. So for example, when you have gases, there's some kind of a place where you just mix those gases and they burn and they generate heat. And once you get the heat, you start working on the fuel cell mode. So it's, so basically it's possible. So as I said, different technologies, but the main advantage of solid oxide fuel cell is flexibility of fuel, because for lower temperature, you can only use hydrogen. If you use any hydrocarbon fuel, methane or other gases, the problem is that those materials are very sensitive to carbon. so they poison it, and the performance goes down and cell degrade. But the good thing about high temperature fuel cells is that you can have flexibility of fuels, and you can supply those fuels directly to those technologies, and they work still. And I will show some reactions there, how it works. Lots of applications, as you also mentioned. So we have land applications, and there we have basically vehicles where this polymer exchange PEM fuel cells are more common. Then we have in buildings where high temperature fuel cells are more common. But nowadays there's because I've been working in a company, Marioff, and I get to know about like different how companies are working nowadays. So there's a huge work where these electric ships, or they will be using these fuel cells for powering their these vessels. So lots of applications there, and then also for satellites, I think it's quite good application. For a hydrogen, probably the most important thing for hydrogen, it has an advantage over other fuel, is that it has very high gravimetric energy density. So in a per weight, you can get lots of energy as compared to other fuels. So it's quite good for that application where the weight is an issue. Yeah, please.
Well, I was just asking about fuel cells and hydrogen motors. How like space/weight efficient are they?
Yeah, I think they are weight efficient, like you're talking about hydrogen, but for space efficient now, they will need large volume for that.
That's true.
Yeah.
But you can use them in aircrafts, for example.
Yes.
Where weight is very important.
Yeah, where weight is more important. Exactly.
That's great.
Yeah. Great. So yeah, lots of applications. I think skip through this this slide, and I skip through this. Let's talk like the real science, what actually happens in the device. So I hope it works. Okay, it's working. So now I'm mainly focusing on high temperature solid oxide fuel cell, and there the main mechanism is kind of the same. We are supplying, let's say, hydrogen fuel on one side, the anode, one electrode, and we are supplying, let's say, oxygen or air on the other side. What happened here is like now at the cathode side, this oxygen gas is reduced, and we get oxygen ions, which can transport through the electrolyte layer in the middle. And this layer, the yellowish layer that you see, that's basically electrically insulator. So basically only ions can move through it. And then when they go to the other side, we have the reaction with hydrogen molecules, and we get water out. So it's the same principle that I showed in the previous slide. It's just the ions are moving in the other direction. So this is how the solid oxide fuel basically.
What makes the dipole oxygen molecule to break down?
Yeah, we have a catalyst. We have catalyst materials. So we have at electrodes, we have some catalyst materials, and that's basically breakdown there. And yeah, here are some possible reactions. What happens, because as I said, in these high temperature solid oxide fuel cells, you can supply different types of fuels. So you are not limited to only hydrogen. You can supply natural gas, syngas. There are so many possibilities. And what happened there is, like, for example, for hydrogen, it's simple, as I explained in the previous slide. But when you supply methane, what happens is at the cathode side, we get hydrogen ions, but we also get like carbon monoxide there, or carbon dioxide, depending on the concentration. And the methane which we are supplying at the anode side, it can form carbon and hydrogen. So once it forms hydrogen, it's simple, the same process, but the carbon can be a trouble in some cases. This is a typical problem in solid oxide fuel cell, is that there's lots of carbon on the anode side, and it just block all the sites for reaction. And so that's one challenge, that we are developing materials that can block this carbon formation, or carbon formation will happen, but we try to avoid agglomeration of this carbon at the anode. So this is a very hot topic of research. How can we avoid carbon formation on electrodes? Because when the carbon formation happens, it covers all the electrodes, and then the gases and the electrodes, their interfaces, so there's less surface area, and surface area is very important for electrodes. I will show in the next slide. Yeah, here, for example, if you see, so we are supplying hydrogen and oxygen. So these electrode layers, they need to be porous. The reason is these gases need to go to those interfaces. So reactions happen at those points where our electrolyte layer or electrode layer, and these gases, they meet each other. So only there the reactions can happen, because there oxygen gas comes, electrode material is needed to catalyze the reaction, and then when the oxygen ions are formed, they need to jump into the electrolyte layer. So they need to happen at those points where all those three are present. So first the gas has to be there, then electrolyte material has to be there, because the ions that are formed, they have to be in this layer, and then the electrode material which catalyzes the reaction. So in this kind of configuration, you might be thinking that only these spots are important ones. There is no reaction happening on these places, because this is the only points where all the gases, electrode material and electrolyte materials are meeting each other. So these are called triple phase boundaries. Only reactions are happening in these things. So electrode need to be porous, because we want gases to go and reach those points where reaction can happen. So that's why this has to be porous. However, our electrolyte should be very dense, because if this layer is porous, then there is a danger, then these gases can cross over and they meet, and it's just like burning, it's like a combustion, like it's not like fuel cell. So we try to avoid any mixing of these gases. So this layer has to be very dense, the middle layer, the electrolyte layer, and the outer layers have to be porous. Next slide will, I think, show it even better. So for example, here you see, so this is our cathode, this is our electrolyte layer. So my emphasis in this slide is basically the reaction, like this reaction, basically happens only at that point where our electrode material, the cathode, our electrolyte, and the gas, they meet each other. So the reaction is only happen at one point, not like in here or other places. So the more we have these kind of points, the higher the reaction rate will be higher. So that's why we make it like a porous structure and mesoporous structure, where we can increase this number of points, which are called triple phase boundaries. So more those points are, the better it is. The reaction rate gets faster. So that's why those nanoparticles or smaller size particles are better, because then we can have larger surface area where we can have larger phase boundaries. So that's, I think, very critical for electrodes. And for the middle layer, which conduct ions, the question is how actually it supports ionic transport. Because for electronic transport, it's a different phenomenon. We know about conductors, the wires they conducted. But for ions, depending on the ion type, they need some kind of defects in the crystal structures of the material so that they can transport through those. And in case of solid oxide fuel cell, we have doped zirconium oxide. This is the atomic structure of zirconium oxide. So basically, this is how we have zirconium atoms surrounded by oxygen atoms around it, no defects as such. But when we dope it with yttrium oxide, what it does is it creates this kind of oxygen vacancy, and it happens because it has different number of their valence numbers are different. So basically, it creates this kind of oxygen vacancies. So those vacancies are the places where these oxygen ions can jump through. So for example, if we see the next slide here, so this is zirconium oxide, this is our dopant yttrium oxide. When we combine them together, they look like this. And as a result, in practice, what happens is oxygen ions which are formed at electrodes, they are jumping through these oxygen vacancies. So it's like a hopping mechanism. They just jump through vacancies. So the higher number of vacancies we have, the faster ionic transport we will have. There will be more channels for those ions to move in there. So that's the good thing. But if we have too much of oxygen ions, then those vacancies starts interacting with each other, and the structure can be collapsed. So there is a limit to that. And depending on the materials, it could be different. But for this material, usually 8% doping is quite typical. But for some other materials, it could be higher. But if you have too much of oxygen vacancies, that's bad. If it's too little, then it will affect your ionic transport. So that's the key message here. And then basically, this oxygen ionic transport it's a thermally activated process. So when we increase the temperature, this ionic transport becomes faster. So it's a temperature dependent process. And we study it with the help of this Arrhenius equation that you see in here. So basically this is the conductivity, ionic conductivity, temperature, then this is the coefficient there, and this is the activation energy. So what energy it needs to activate the process. And then we have natural gas constant and the temperature. So without going into details, in the plot you can see that's like Arrhenius plot. On the x-axis is the inverse of temperature. On the y-axis we have log of temperature. So the lines are just showing that when we increase temperature, ionic conductivity improve. And when you use this, the same coefficients that we have there, like the same units, then the slope of those lines tell you the activation energy. So it tells about the quality of material, that if the activation energy is lower, it means that you need less energy to activate this process. But if the activation energy is very high, it means that in order to activate those ionic transport, you need larger amount of energy so that this process happens. So the key message is that basically this ionic transport process is temperature dependent. When we increase temperature, ionic transport gets better. And that's one of the reasons you will see in the next slide why I'm talking about this, that why we have high temperature fuel cells, why don't we operate the same fuel cells at lower temperature?
You want to increase the power.
Sorry?
You want to increase the power.
The power, yeah. So, yeah.
Sorry, I was in the middle of the phone
Yeah.
call, but how dependent is it from how much do you dope the material?
How much we dope? So about 8%, like in this case. Not much, but I think there is another type of material, cerium oxide. I think there the doping can be higher, up to 20%, but over 30% the structure collapse, I think. So yeah, so I think that was mainly about. So main message in the previous slide was the ionic transport was temperature dependent. We increase temperature, ionic transport becomes faster. So that's the key message. Similarly, at electrodes, as I emphasized in previous slide, that the reactions actually happen only at three-phase boundary. So now I'm listing here like all the steps what actually happen there. The first thing is, let's say we are talking about anode where we are supplying the fuel. So first, when the hydrogen molecules come to the anode, first, this is the figure there, which is like showing the particles where we have this three-phase boundary. So first thing is the hydrogen molecule need to be absorbed on the surface of the electrode material. So once it's absorbed on the material, it dissociate, and then it diffuse towards this reaction site, which is a three-phase boundary. So this is the third step, and at that step, reaction happens, and electrons goes through the metal side, and the oxygen ions which are coming from the electrolyte, from cathode to electrolyte, they react with this hydrogen, and we get water. And electrons go through the metals, the nickel oxide, so it's nickel, so they go out. So these are the steps. And the water which is formed, we need to make sure that this water also leaves the space, because if we have too much water, it will flood the fuel cell. So we have to make sure that it's a porous structure, and the water which is formed, it need to also leave the space there, so that the reaction can happen efficiently. Exactly the same thing happens on the other electrode, where we are supplying oxygen molecules basically, or air. In case if you supply air, nitrogen do nothing. It's only the 20% of oxygen which does the reaction. And if you supply pure oxygen, then oxygen is there. Again, the oxygen need to be absorbed on the electrode surface. It need to be dissociated. It need to migrate or diffuse towards the reaction site, which is the three-phase boundary, which is basically like these points where we have cathode, electrolyte, and like these boundaries. So at those places, what happens is reaction happens, and as a result, oxygen ions go into the electrolyte layer. So these are the steps. Any question at this point, or it's kind of clear, I guess? Okay.
How
So,
big is the fuel cell in real life?
Yeah, these cells are not so thick. These electrode layers are, from functional point of view, they can be only few microns, like 1 micron to 10 micrometer is sufficient for the process. But the thing is, like if the cells are so thin, then mechanically they are not so stable. So usually what we do is one of those 3 layers are made like thicker, let's say about 300 micrometer, and the other layers are few micrometers. So mostly there are different structural configurations. I think that's the next slide here. Yeah, that's the next slide. That it can be electrolyte supported cells when we have huge electrolyte. So yellow color here is the electrolyte. So we can make a very thick electrolyte and very thin electrodes. So it's called electrolyte supported cell. The other configuration is that we make our anode very thick, and the other layers can be made only few microns. So that will be anode supported cell. Similarly, we can make cathode supported cell. And it was found that out of these 3, the most, actually, I think there is a question there. Okay, I don't ask this question. So anyway, so basically, out of those 3, the most efficient ones are anode supported. And the reason for that is, for electrolyte supported cells, when we have very thick electrolyte layer, the ions move such a large distance, so we have huge ohmic losses. So ideally, this layer should be, the only function this is doing is to separate electrons. We want to avoid any gas crossover. We don't want any electronic leakage through it. Otherwise, ideally speaking, this should be as thin as possible. So that's how it should be. So when we have thicker layers, we have ohmic losses, which is kind of reducing the cell performance. In case of cathode, this is better than the first one, but the problem is we have 2 choices if you compare B and C. On one side we have oxygen molecules, the other side we have hydrogen molecules. And as we know that hydrogen molecule size is much smaller, so it's easier for them that even though the layer is thicker, they will manage to penetrate through the layer and reach the reaction site. For oxygen, it's relatively harder to reach that site, so we have higher losses when we have really large cathodes. So that's why the most efficient one are the anode supported ones. But nowadays there are some new configurations coming up which are called metal supported. So the idea is that why should we make the functional layer so thick just to make it mechanically stable? Let's use some other porous metal substrate which will make it mechanically strong, and it's conductive, and so there are not much losses, and we make all those 3 layers thin, but thin enough that they do their functions efficiently, that they don't let the gas cross over, and dense enough that ionic transport also happen efficiently.
If you want to test new materials, so how to build those fuel cells, can you do it here in Otaniemen?
Yeah, this is exactly, I will briefly tell what we are doing in our group. So yeah, this is exactly what we are doing. We are trying new materials, and we are trying new structural configurations also. So that's what we do, and you're welcome if you are interested to have a visit. I think we can arrange, because now I hope COVID situation is getting better. So I think if you are interested, I will be happy to show you our facilities around. Yeah. Okay. No, it's in Nanotalo. It's yeah. So it's old main building. So in front of that we have Nanotalo. And then cells can be in different structural configurations. They can be made in tubular structures, like this kind of tubular structures. One gas is flowing in the middle and the other in the outer surface, or it can be planar structures like these kind of planar structures. So these are typical fuel cells, how they look like. And I'll just show the data sheet of those. So if you buy a fuel cell from a market, you get this kind of a technical data sheet. So you should check about, okay, sizes are important. You get that kind of information. The thickness of those layers, that's kind of typical, good to see. You should check the materials. And then also the thermal expansion coefficients are important, because somehow if you are using some kind of a fuel cell which have materials with different thermal expansion coefficients, then when you heat them at higher temperatures, it means that there are higher thermal stresses in the cell, because these materials have different thermal expansion coefficients. And at higher temperature, there are thermal stresses in the cell depending on those. But this is how, and in Finland we have Elcogen. So these cells are from Elcogen. I think it's a Finnish Estonian company that makes fuel cells. And yeah, okay, let me check the time, yes. And then some key challenges there is the high temperature for solid oxide fuel cell, because then at high temperature we have limited choice of materials, degradation issues. So now the researchers are trying to reduce its temperature to something between 400 to 600, because it's high enough that we can use different fuels directly, but at the same time we can try different materials, and degradation is not that big issue at 4 to 600 degrees, but at higher temperatures it's really a big issue. So these are, the main thing is the thing. And then also I think you asked about the vehicles. So the thing is, like, the largest startup time is the issue. So when we reduce the temperature, the startup time also goes down. So these are also some advantages. So now the idea is to try new materials there, getting the same high performance at lower temperature, that the performance that we get at high temperature. But that's the challenge, because when we reduce temperature, the performance also goes down. And why? Because all those processes, especially the ionic transport process, is a thermal activated process. At high temperature, it's very good transport, but lower temperature transport goes lower and the losses are higher. And that's the key research that we are doing, and that I briefly cover in later slides.
So it's kind of optimization problem, very many parameters.
Yeah.
Affect differently.
Yeah, and it's somehow we need new materials that can offer higher ionic transport at lower temperature, and there are different ways to do it. And for example, we are using some composite materials to achieve the same thing. I will present here, and then I think this is, I briefly tell. So then we have lots of cells that we put them in series, make stacks, and from stacks we make fuel cell systems. So that's generally how we build the systems. Okay, lots of companies, I think VTT is doing research on this, then ABB are working on, Convion are selling fuel cell systems in Finland, Elcogen are making cells and also stacks. So these are in Finland, and then there are really big players in the world, like they are building systems in really huge sizes. So all those things are there. So I skipped that part. Yeah, and then electric vehicle versus battery vehicle, that's my favorite topic. So both have advantages and disadvantages. Briefly speaking, I think for short distances, I think batteries vehicles are good, but they are not good for very long distances. And but I think for large distances, this fuel cell vehicles could be quite good. So yeah, time is limited, so I don't go in detail there, but I keep my focus on fuel cell. Okay, this is briefly about the summary. So now you know what are fuel cells. They are devices that convert chemical energy into electrical energy, and then basically there are different types of those, and they have different applications, and the market is growing. And there is one saying by that I believe fuel cells could end the 100-year reign of internal combustion engine, because still we see all those cars are mostly internal combustion engine, but now fuel cells are coming also for vehicles application. And the next part, I will be talking about our research that we do at Aalto University, so that you know what we are doing in there. And so this is our research group, and in our group, yeah, so we have Professor Peter Lund is the head of the unit, and then I'm working, and I'm docent and academy research fellow. Then Sainas, my PhD student, and then Piru has been doing his master's thesis, and then Sini, Alpi, and then we have two other, Magnus and Axel. So that's like our fuel cell team, and mostly our projects are funded by Academy of Finland. So I have this academy research fellowship as a 5 years project, and then in our group, basically we are doing from really nanomaterials. We make synthesized nanomaterials or materials for fuel cell application, and then we characterize those materials. We see their properties, they have the right properties, and then we make devices from those materials by different methods. In the past, we have been using pressing methods, but now we are focusing on digital printing, 3D printing, inkjet printing. So we are focusing on different printing methods. And once the devices are made, we do their characterization. So from very nano scale to macro scale, we do all those steps in our labs. And there are different characterization techniques. So I just skipped those one. But what are the key research areas? As I said, we synthesize nanomaterials which look like this. So we are doing quite much chemistry actually in our labs, although we are in the physics department, but the fields are so multidisciplinary that you need to understand chemistry as well. And then we make our devices. Basically, this is screen printing, and you see a 3D printer there. And then our cells give higher performance at lower temperature. And the reason is multi-ionic transport, that we allow multiple ions to transport through the electrolyte layer, but they do not, there are different channels for those. So we are not relying on only one ionic species, but then there are other ionic ions that are transported in the electrolyte. And then we have different characterization techniques. Okay, I skipped that one. We have two themes. So the surprise element is coming. So basically, any electrochemical device, as I said, also fuel cell, they have three layers. We have anode, cathode, and electrolyte. And whole my lecture, I was emphasizing about electrolyte and electrode processes. But then we are also working on a really novel, unique concept. We are working on a single layer fuel cell. So instead of these three layers, it's just one layer, and it does all the functioning. And logically speaking, it should not work. It should short circuit it. Like the question is why, how it's working, and we don't know how it's working, but it's working. And now we are doing systematic studies to find out like what are the processes, and there we develop our understanding. But still, I would say it's quite speculative. We need like further investigation to find out. So we have different speculations there that since these materials are semiconductor materials, maybe they form some junctions in between, and the built-in voltages there can prevent it. But still, personally, I believe in solid experimental evidences. Then we can say exactly that's the reason. But so far, we don't have those solid experimental evidences. But the device is working. That's the good thing.
How did you start the examination in the first place?
Yeah, it started with, we had one collaborator, and he has been trying different configurations, and we just tried these cells, and it's working. But then we started developing because those cells were not so efficient. But then we tried some better materials. This layer is a mixture of electrolyte and electrolyte materials. So it's a mixture of both, but their ionic transport properties are much better. And the electronic properties are not so good. They are wide bandgap materials, and they give quite good fuel cell reactions. So we get performances up to 1 watt per square centimeter. So quite high performances we have achieved with this one. So that's a surprise thing, and quite a new thing in research. So that's the thing. But the good thing about this single layer is it has lots of advantages, because as I said, when we have three layers, they have different materials, different thermal expansion coefficients. At higher temperature, we have higher thermal stresses. In single layer, it's a single layer, so there are not so much stresses. So it has improved thermal stability. And also another good thing about this single layer cell is that if you switch the gases, if you switch air on the other side and fuel on the other side, it still works. It just changes its polarity. So it's amazing. Like the changing the area, exactly. And it's quite good for the fuel cell system design, that now we have more flexible, because in typical three-layer structures, due to the materials limitations, the anode materials are different from the cathode materials. You cannot switch gases. It will not work that way. But for single layers, it's a good thing because it's homogeneous layers. So there are some advantages. So I briefly, but the thing is like why these cells are not short circuiting. We are trying to figure this out. We have different speculations. Okay, this is a very basic simulation. So I don't know if this is happening or not, but we are supplying gases and we think that we have oxygen ions formation, okay, and hydrogen ions formation, and in between in the cell, it forms water, and we get the electricity. So this is one like possibility, but I don't think so. It happens, but most likely, I think we have some. Since these are semiconductor materials, so there are some energy band gap engineering happens, and those kind of prevent the short circuiting, prevent the electronic leakage through the cells. So it's a more complicated concept, but we are still working on this. Okay, then another way to reduce the temperature is that we use ceramic, we composite materials. So we make some kind of materials. So basically in this equation, as you can see that in order to reduce its losses, either we should reduce the thickness of the electrolyte layer. So now I'm talking about three-layer cells. So one idea is that either we decrease the thickness of the fuel cell, or we can make it more conductive if their properties. So our approach is basically for both. in order to improve ionic conductivity, we make these ceramic nanocomposite materials, which are basically like this. So it's a composite materials that allow multi-ionic conduction at the same time. So now we can have different ions conducting at the same time, and as a result, the ionic conductivity of this layer is much improved. And we have actually record high ionic conductivity materials in our lab, which is 0.5 Siemens per centimeter. So that's kind of really high, like really top materials. So these are the materials. So we get about 0.5 Siemens per centimeter, and our study was published in a quite nice journal, Materials Today, and that was a breakthrough for in our field. And using those materials, we get about 1.1 watt per square centimeter at 550, which is like lower temperature, because the typical solid oxide fuel cells, they used at 800 or 900. So now it's a significant difference in temperature. So that's one great thing. But there we realized this is the cross section of our cell. This is a scanning electron image of our cell, and one of the best results reported in the literature. So when we compare them, the best result was 2 watt per square centimeter at 550, and we are about half of it. And then if we look at the geometries, we find out that their cell is much thinner, especially if you look at the electrolyte. It's only 9 micrometer thick electrolyte, and our electrolyte is 300 micrometer. So that's so thick. So if we can reduce the thickness of our electrolyte layer, then there is a possibility that we can make a new record, because if you look at the properties of the materials, which is ionic conductivity, our ionic conductivity is orders of magnitude better than them. So we are 0.5 Siemens per centimeter, and their ionic conductivity is not so good. So that's why they need to reduce the thickness so much. But even if we get to 20 micrometer with this high ionic conductivity, we envision performance beyond state of the art. So that's what we are thinking. So that's our key focus here, please.
What is stopping you from going as thin as like
Yeah,
micrometers?
yeah, that's a very good question. That's exactly the next slide is basically in the past we have been doing it with some pressing methods. So basically we have these powders, nanopowders, and we press them. So this is how we fabricate those devices. So and somehow this method doesn't allow us to make like thinner layers, because it's the method is kind of stopping us from making it the thinner layers. So basically the printing technologies or some vapor phase deposition techniques, you can make thinner layers. But the first challenge there is you have to make the paste of those. If you want to print them, it has to be some paste or some inks of those materials. So the first challenge for us is to make inks of our materials. So we have the powders which have the right properties, but the first challenge is to make inks or the paste of those materials, and then with the help of screen printing or inkjet printing, and I have 3D printing. I hope it works. So this is a 3D printer printing our materials. Work, please. Okay, this is just extruding like those materials. So we need this kind of printing technologies to reduce the thickness, and now we are actually doing it. And now we are there are some challenges still there, because when we develop our inks, their properties also goes down. The ionic conductivity is not that good anymore of the paste, so we are trying to improve it. So that's what our current research we are focusing on.
Can I put it this way? So you are kind of using macro scale device in order to make something micro scale.
Yeah, basically. Yeah, that's right. Yes. So basically, these layers that we are forming, they are, I think like for this 3D printers, nozzle size is much larger, but it's about a few microns are the thickness of those layers that we get from here. So typically, I think we are aiming about 20 micron, and then gradually we will optimize it. But at the moment, we try to make it like a little bit thick, but thin enough that we get high performance. So that's one thing. And then we are also using inkjet printing. That's so we can make skeleton with the 3D printer, and we can infiltrate materials because we need composite materials.
If you compare with the technology used in micronova, what is the basic key difference between?
Yeah. So in micronova, you mean in VTT? Like they I think they are using conventional fuel cells. I think especially, actually they work on both low temperature PEM fuel cells also, There is really a different case altogether, and I think they're also working on solid oxide fuel cells also, but they do not do the cell fabrication by themselves. I think, to my understanding, Elcogen is the company who make this solid oxide fuel cells, and there are no other companies, I think. So there are, I think, doing research also on lower temperature, like the PEM fuel cells, but I don't know exactly what is the status there. But okay, so basically that's about the presentation. I think it's 45 minutes. So I will be happy if you have any question about fuel cells or what we are doing. Yeah, please.
What stops you from like sanding the membrane or like electrolyte? What stops you making it thinner?
Thinner, yeah, yeah. So basically, it's a method, fabrication method, because we have been using this kind of technique. And the thing is, like, if you want to reduce the thickness, this method doesn't allow us controlling the thickness precisely. We have tried it, but somehow didn't fail because somehow it's lots of manual steps are involved. And when you are talking about this few microns like scale, you need better control on your fabrication method. And another reason, so that was basically limiting us. But another reason we have switched to printing technologies is that this method is not upscalable either. Because when this technology is good, it should be good for mass production. And with these methods, the idea is that we put the powders and we put lots of load on top of it. So for small cells, for example, if you want to press with 250 megapascal, we can put 4 tons on it. But let's say if you want to make larger cells, we need huge weight to make it. So the process is slow, not very practical. But with the printing, you can make cells in a larger quantity and like roll to roll. So you can make it in a production can be faster. So for commercialization, we think that printing is better, but also the advantages that we can control the thickness there also. But nowadays, it's also very hot topic in research that making layers even hundreds of nanometer thick layers. But for that one, printing technologies are not so good because printing technologies are mostly few microns thicknesses. For that, this ALD, I think it's a Finnish innovation. I think 1980s, some professor in University of Helsinki, I think they invented atomic layer deposition techniques, for example, or we have pulse laser deposition techniques. So these are physical vapor deposition techniques that you make layers by atomic depositions. So with those methods, of course, it's easy to say then actually do it. It's lots of research questions there. But I think with those techniques, we can make very thin layers. And I'm talking about hundreds of nanometer. And if we can make dense enough layers that can prevent the gas crossover, then I think we can get really high performances. Then we are talking about 4 or 5 watts per square centimeter. So overall, the good thing about fuel cell devices is it's a very high power density devices. So you get really high power per square centimeter, for example. So so that's the advantage of this. For solar cells, for example, because I did my doctoral studies in solar cells, I've been working on it. It's a promising technology, but you need larger area to get the same power. But the fuel cells, I think those are quite good devices in that sense. And then the good thing about these cells are also like the solid oxide fuel cell and these materials that we are working on, that they are also good for electrolyzers. So we can also use them for hydrogen production. We haven't been doing it much research in our group, but now actually next week I'm going to Denmark for some research visit for 2 weeks. And there the main focus is on electrolyzers, that I will be taking some of my samples there because they have been doing electrolyzer studies quite a lot. And then I will come back and try to build the same setup here. So we are thinking to continue with electrolyzer studies using the same materials. Yeah, so between universities, yes. Yeah, please.
Currently, from an economic standpoint, what is the state of fuel cells?
Yeah, I think
How
they're
expensive are they?
I think they're. I don't know exact figures, but I think the main thing is like they're expensive. They're not expensive. And I visited Elcogen a couple of years ago, and I think they also told us that somehow the cells were quite expensive, but prices are going down, and but still I think they are expensive. But if you compare with, let's say, lithium-ion batteries, for example, so the lithium is getting more depleted. So the prices of lithium-ion batteries is predicted that in future they will get more expensive, but the fuel cells cost trends are going down. So I think I don't know exactly when, but at some point of time they will be very competitive also, and so the prices are going down. Yep. Any other comment or question?
So if you want to work in this field in the future, you should study physics and chemistry.
Yes, physics and chemistry. Yes, that's right. Yeah, it's called like a branch of chemistry. It's like electrochemistry. So it's like electron chemistry and physics. So yeah, it's so multidisciplinary because this nanoscience, it involves basically everything, material physics and yeah. Yeah, but it's very nice area to work on, and I suggest like if you're interested in physics and chemistry, and in Aalto University, I think that will be very nice. We are doing quite good research, and I think in the physics department we are the only group working on energy technologies basically, and I think very important topic to work on, especially if you look at climate change and the global warming. So I think it's very important to work on clean energy technologies.
That was my next question. That how do you feel working in this pioneering field for solving these technical problems?
Yeah, I so basically like you mean like how I feel like working on?
Yes.
Yeah, I think yeah very much because I basically my background is such that in my bachelor studies I did robotics. So that's my bachelor. I did robotics. I was very interested in robots, and then I'm from Pakistan, and there we made some robots and we participated in some international robot contest, and I made some robots that play basketball, and we won some national contest, and in Beijing we went there for international robot contest. But there I heard about nano robots, that their robots can be very nano sized and you can do surgeries without cutting the body and with the nano robots. And then I decided to come to Finland because there was a program. It was Helsinki University of Technology at that time, and I came here to study nanotechnology. But during that time in my master's in 2006, I realized that nanotechnology has application in many areas, and by that time I realized that energy is the biggest challenge humanity is facing. And I was thinking that, okay, energy is important to study and nanotechnology can be applied there. So then I started working on energy, and I did my master's thesis in micronova and on silicon solar cells. And then I continued my research on solar cells mostly for next 6 years. I did my doctoral studies on solar cells, and then also work in industry for some time. And then from 2014, I started working on fuel cells. It's a new topic for me, but then I realized by that time that it has a huge potential, and especially these electrolyzers for hydrogen production and these fuel cells. I think these are they can play a key role in this energy transition. So that's why I think it's a very important area to work on. So that motivates me to like focus on energy and working on these sustainable technologies.
It's very interesting